Warm welcome to all of you in today's webinar on stealth laser dicing process hosted by CMC and will be presented by Mr. Richard Boardman from GDSI. My name is Abdul Qadir Ehsan and I'm a MEMS staff scientist at CMC Microsystems and I will be your host today for this virtual event. All the participants are muted by default. There will be a dedicated Q&A session at the end of the webinar. So uh, you are all welcome to ask question in that Q&A session or along the webinar as we go. It's totally a very interactive session. So you have both options. You can also ask your question through the chat window that will be monitored along the webinar as we go. So first, I will give a brief introduction of CMC Microsystem, that is who we are and what we do. Then I will relinquish this forum to Richard, who will present his company and who will also shed the light on today's webinar topic, which is stealth laser dicing technology or process. Finally, we will have a Q&A session. CMC Microsystems is a not-for-profit organization with a mission to lower barriers to technology adoption. CMC provides services to simplify access and reduce costs to advanced technologies such as microelectronics, photonics, MEMS, nanofabrication, artificial intelligence, and quantum technology. We are the managers for Canada's National Design Network, CNDN. In our mission, we deliver micro and nano innovation capabilities across Canada. And broadly speaking, we deals with technologies that provide infrastructure for innovation and are critical to enabling Canada's growing digital economy. So Canada's strategic direction aims to maximize impact on Canadian research, innovation, and economic growth. Microelectronics, photonics, optoelectronics, and micromachining, embedded software, and nanoscale technologies are enabling progress in numerous specific scientific disciplines. These strategic technologies also contribute to innovative application in many industrial sectors, namely clean technology, advanced manufacturing, digital industries, health sciences, and agri-food. The National Design Network is a Canada-wide collaboration between 67 universities and colleges. It connects 10,000 academic participants with 1,000 companies to design, fabricate, and test microsystems prototypes. This microsystem prototype systems. This map shows the depth of the participation across Canada and the outcome that we have achieved yet. We also provide our clients a competitive advantage by bringing our global supply partners and network to their very doorstep. The infrastructure and services we provide is divided into three main categories, namely CAD, FAB, and lab. In CAD, we deliver design tools, platform, tech trainings, as well as compute infrastructure to design and develop macro and nano system prototypes. We deliver these capabilities either through our cloud infrastructure or on the user desktop. In Fab, we also provide multi-project wafer services through a global supply chain. We also provide packaging and assembly services, fabrication and travel assistance to manufacture prototypes in commercial labs or in university-based labs. Under the lab services, we provide short-term access to development platforms, test equipment to validate and emulate system test prototypes. The technologies that CMC supports include microelectronics, MEMS, photonics, microfluidics, and embedded system. All of these are enabled through various offerings and programs that we have. And one of them is packaging technologies. So these are some examples of CMC packaging technologies offering that our clients have benefited through our global supply chain partners, and and soon you will see GDSI among them offering a still laser dicing process. Thank you. Now I will hand over this forum to Rich. Rich, please introduce yourself and your company and shed the light on today's webinar topic. Over to you, Rich. Thank you.
All right. Thank you for the introduction, Kedar. I do appreciate it. A little bit about my background. I've been involved with matters related to dicing, grinding, and polishing of wafers or substrates since 2006. So I have experience with mechanical dicing, stealth dicing, laser ablation, grinding, and polishing. And then as far as my company, GDSI, we are based in Silicon Valley. We've been around for the last 30 years, and our core competencies are any matters related to outsourced wafer dicing, grinding, polishing, stealth dicing. We also offer support for pick and place and automated optical inspection. As I mentioned previously, we've been around for 30 years, so we are not new to the industry. We are experts in our field. A little bit about our accreditations. We have ISO, ITAR, and for more sensitive matters, we're also a Cat 1A with DMEA for trusted projects. So some of the key offerings that we have, we've already talked about stealth, traditional mechanical dicing, die grinding, wafer grinding. We operate in a multitude of industries. So, at our inception, typically it was just the semiconductor industry, but over the last 30 years, we've grown into many other industry sectors as well, which are, not limited to, but do include defense, medical, optical, communications, quantum chips, artificial intelligence, 5G, to name a few. We're very adept at handling a multitude of materials. We're going to focus mostly on silicon today, but we also have a wide expertise in materials such as silicon carbide, glass, fused silica quartz, hard materials, sapphire as well, GaN, PZT. And then you can see here a little bit about the various applications we support. Most of what we'll chat about today with regard to stealth dicing will focus around MEMS, silicon photonics, and sensor-based devices. So why we're all here, if you are attending this webinar today, you obviously would like to learn a little bit more about stealth dicing and what is that other than a pretty cool name. So stealth is a laser dicing process. It's a registered trademark of Hamamatsu Photonics. They make the heart of the laser dicing tool, the laser head itself. So here's the agenda. We'll talk about what stealth is, what applications it can enable, some of the keys to using stealth. There are some design rules that need to be adhered to, so it's always good to know those up front. We can talk about the process window, how we process from the front side, the back side, and some other processes as well. So in a nutshell, what is stealth? So it's 100% dry laser singulation process. It's not an ablative laser process. With laser ablation, it is necessary to deposit a coating on the surface of the wafer. You focus the laser light on this top surface of the wafer, and slag and recast and debris is created. And then downstream, before the wafer is removed from the laser saw, you have to do a wash step to remove that protective coating. For devices that are sensitive to water or debris or slag or recast, that laser ablation process is not a good fit. And this is where stealth really comes in. So in essence, what we're doing, if you look at this sidewall image that we have right here, we're using the top surface of the silicon as a secondary focusing lens for the laser. And then we're creating these modification layers beneath the surface. So we'll typically start at the bottom where you can see my cursor right now, and we'll build up. You know, depending on the thickness of the silicon will dictate how many modification passes we need to induce. And then once that laser modification process is complete, if you were to look at the wafer on the tool at that point, it would almost look as though nothing had happened. The magic with stealth is basically you take this wafer that's been modified, you put it on a tape expansion system, and you stretch the tape in all directions uniformly, and then you get separated die on the tape. And I have some images that I'll show with you guys later in the presentation on that. And just to reiterate what Kedar said at the beginning of this presentation, if you guys have any questions, we're really happy to have an open discussion as questions come up. So feel free to, you know, unmute yourself and drop in those questions anytime, and we can handle them on a case-by-case basis. So what you're looking at here with these images is after the tape expansion step has been completed, you can see the singulated die on tape. So as I mentioned previously, you know, there's no water. This is a completely dry singulation method. There's no debris that's generated like you would see with a traditional mechanical dicing process. You've got an extremely dry and particle-free singulation process here. So, you know, for MEMS devices, this was really where the inception of stealth came from in about 2007 and 2008. MEMS devices came along and they had sensitivities to the vibration from the mechanical dicing process and the sawdust that was generated, and that was an absolute showstopper. So having a dry and particle-free singulation method was hugely helpful. Other industries that benefit from this, a lot of biochips, gene sequencing chips, they also cannot get wet, and they benefit greatly from stealth. Multi-project wafers are another great case for the benefits of stealth. If you take a look right here in my middle picture and bottom picture, you'll see that you've got different die sizes on one wafer. With a mechanical dicing process, that would require perhaps sacrificial die. You would have to give up some die and dice through them to singulate other die on the wafer. And you would certainly also have to do multiple sub-dicing and remounting steps. I mean, in certain cases, you know, 10, 15 remounts for a complex multi-project wafer layout could be possible. Whereas with stealth, we have the ability to turn on and off the laser beam. In essence, we can create T-junctions, and then you're able to, in one shot, singulate all the die on the wafer with varying die sizes on there. So it's a very disruptive technology in that aspect. Another nice application of stealth is with traditional mechanical dicing, you will always have some kind of kerf loss associated with the blade. And that kerf loss will increase as the wafer thickness increases. And in small die applications, that can affect, in terms of thousands of die, how many die are able to be populated on the wafer. Stealth is a zero kerf process and will allow you to populate many more die on the wafer as a result of that. So this is really where the rubber meets the road. It would be an inaccurate statement to say if you have a wafer right now that is designed for mechanical dicing, that it would directly port over to a stealth dicing process. Given that this this process is using the top surface of the material as a secondary focusing lens for the laser. It requires that material absorb and not diffuse the laser light. So in direct tandem with that, wafer resistivity is crucial. If we have resistivity on the wafer of lower than 1 ohm centimeter, it typically doesn't allow us to focus the laser light beneath the surface, create those stealth layers that you saw in the sidewall of the wafer a couple of slides ago, and then allow you to separate the wafer post stealth dicing processing. So if you do have a wafer that's lower than 1 ohm centimeter in terms of resistivity, what will happen is when you go to the tape expansion step, the die will not separate, or you might have some that separate and some that don't, but it won't be the beautiful, clean separation and 100% singulation that we would expect. Another thing that's key as far as material design rules go is the crystal structure. We typically prefer, or I should say the laser prefers, silicon with a 100 crystal structure. And the reason for that is if you go off axis on the silicon, what will happen is you'll see not a beautiful clean separation in the center of the street, but almost like a lightning bolt. It's separating on the plane of the wafer itself. Things such as cavities and gaps within the silicon will prevent the laser transmission. What the laser is looking for is a uniform flat surface of silicon across the wafer in order to transmit the stealth dicing layer underneath the silicon. If we have cavities or gaps, that laser light transmission will be interrupted. And then again, going to the post singulation step, the tape expansion step, we won't have uniform singulation there. So in this case, we may have to dice from the front and the back side of the wafer. Now you might say, well, how do you see through the wafer? So on the stealth dicing laser system that we have an IR camera that's able to look through the silicon, and we can align to features on the front side of the wafer, and we can dice from the back side of the wafer. So what that allows us to do is when we have devices with very narrow streets, there is another design rule that we have that we need to have 40% of the overall wafer thickness as a clear street at the surface. So in essence, if you were to supply a 100 micron thick wafer, we would need a 40 micron street in order to be able to put in enough stealth modification layers beneath the surface to have successful die separation afterwards. So a lot of customers will give full thickness wafers for this process. So then we're into the orders of magnitude of 700 or 800 micron thick. So if we extrapolate out on the math, we're looking at asking for streets that could be up to 320 microns wide, and that's pretty wide and not always able to be offered. So at that point, we are able to turn the wafer over if the backside of the silicon has a suitable surface. And what I mean by that is finer than a 2000 mesh ground finish. So that's right around 200 angstroms of roughness. What we are able to do is concentrate the laser light from the backside, put our modification layers in. We've already aligned from the front side features, which we've looked through with the IR camera, and then we're able to process and do die separation successfully. So things that are not friendly to the stealth process are things that either inhibit the laser light to transmit or reflect the laser light. So things that inhibit the laser light to transmit will be either too low of a wafer resistivity. You could also have perhaps some very thick oxides on there, you know, perhaps to the order of 9 or 10 microns. That will give some issues with the laser light transmitting. You could also have metals or films that will reflect the laser light. And this characterizes itself by showing up as ablation on the front side of the wafer. And that is bad because that will also potentially splatter up and negatively affect the lens on the laser. And that's not something that we're looking for. So some of the nuances to the stealth process now, as I mentioned previously, we're able to switch the beam on and off. So you can see it to cut octagonal shapes, or, you know, this was more experimental right here. We did a modified coring of a wafer. So we cut in multiple channels to take a 8-inch wafer and core it down to a 6-inch wafer. That's not really what stealth is intended for, but was just kind of a neat little science experiment. More of the day-to-day application of the on and off of the beam you can see on this quarter wafer right here with the multiple die sizes that we're able to fully singulate, do one tape expansion step, and yield everything out of this quarter wafer in one shot. So right here, what we have is some images of the top side of a wafer post-stealth. So for those of you that have experience with mechanical dicing, you'll notice that on this image that we're showing, you know, you see zero topside chipping here. And it's a true statement to say that stealth can offer, you know, almost zero topside and backside chipping. You might see a slight meandering of the beam within 1 to 2 microns, but you know you're looking at, you know, absolutely pristine quality on the surface and backside of the die. And then again, right here, you can see, just going back to my last statement when we were talking about the modification layers beneath the silicon, you can see this is the active area at the top. This is the top side of the wafer, and we've got a waveguide right here, or a laser. And we've got the modification layers beneath. And, you know, at the surface here, it's going to be a beautiful facet quality, you know, just fantastic right there. No debris, and just great sidewall quality. And then obviously we have a little bit of roughness to the stealth layers beneath there. We're also able to cut railroad tracks. So as I've mentioned before, stealth is a zero curve process. So perhaps you have an application where, you know, your die are designed to have a section of material removed to get the overarching final die size that you need. So within reason, we are able to do that. And what I mean when I say within reason is this section that you look at right here will be around 200 microns wide, and we will make 2 cuts in the same street. And then we will leave that sliver of silicon within the street itself, and it would separate at the tape expansion step. Now, if we were to go narrower than 200 micron, what we may see is that sliver sticking to one side of the die or the other. So that's the downside to potentially doing this process. But down to around a 200 micron sliver, it works in production. It's a repeatable process. And we're always open to, you know, to speak a little bit more to developmental projects. We're always open to developmental projects. We have, you know, some customers that run production and load us with 50, 100 wafers a day. We have some customers who send us a wafer or 2 a year. So, you know, if there's something that you're looking to do on a development basis, you know, we're more than happy to help with that. We're looking to push the bleeding edge of what's available in terms of anything to do with dicing, grinding, or polishing, or laser dicing, stealth dicing. So why is stealth? Why would somebody consider a stealth process? If you have devices that are sensitive to water or debris or saw vibration in any way, if you cannot tolerate a laser ablation process that requires a surface coating on the wafer, if you cannot tolerate slag or recast, for your devices. If you have MPW wafers that right now you are having to either sacrifice die or do a very drawn out and painstaking mechanical dicing process with multiple remounts. If you're looking to, perhaps you're you have tiny devices, say less than 1 millimeter square, RFID, for example, and you need to figure out how to populate more die on the wafer. Stealth would be a great fit for that application. So a little bit more about how GDSI can enable you right here. As I mentioned previously, we can help out on fast turn prototype projects. Perhaps you already do dicing or grinding or polishing in-house and you're just looking for additional capacity support. With the COVID world that we live in right now, it's not fast to get new equipment. It's typically taking double the time. So we could help with that. If you are an organization that doesn't have perhaps any expertise in dicing, grinding, or polishing, and you want to enact and draw in subject matter experts to help with those projects, we have those on our engineering staff. As I mentioned previously, we've been in business for 30 years. So we're really looking to partner with you on anything related to, dicing, grinding, or polishing. Speaking a little bit more to the bleeding edge processes. So stealth right now is the most leading edge technology we have. What we're looking at bringing in on our roadmap next is laser filamentation for optically clear materials. So that is a process that theoretically could give even nicer sidewall quality than stealth. It's also a dry process. It works downstream with a mechanical braking step rather than a tape expansion step, because those hard and amorphous materials, tape expansion is not able to exert enough force to separate the die post-processing. We're also looking at laser ablation for low-K grooving, also for silicon carbide singulation applications. So, we're really trying to focus on what those next generation processes are, where the markets are going, and we're deeply involved in that. So if you have any questions, please reach out.